Okay, so this week the main reading is going to be chapters 9 and 10 of Sutter, and then chapter 1.4 and 6 of Nielsen and Schwang, and then a couple great articles. I would especially point you to the second one from Schwang on doing Shor's factorization using NMR, and we'll talk about that paper on Wednesday. Okay, so to start our discussion of algorithms, we're going to start with a toy problem. But just by way of preface, now that we sort of understand qubits and the operations that they can perform, it's time to start stringing them together to actually do something with them. All of the qubits or the algorithms that we're going to be talking about today are implemented using logical qubits, not physical qubits, so that's something to keep in mind. And all of the gates that are used to do these algorithms are the ones that we've seen before. But of course, in any physical hardware quantum computer, they might look different because the way the actions need to be implemented are going to be dependent on the physical realization of the qubits. Okay, so like I said, we're going to start with this toy problem that was introduced by Deutsch in 1985. And the problem is, I have a function, it takes some binary input, 0 and 1, and it produces a binary output, 0 or 1. And there's kind of 4 possibilities. The first 2 possibilities are both of my inputs, 0 and 1, map to 0, or both of my inputs, 0 and 1, map to 1. The alternatives are my inputs pass through unchanged, or the inputs are exchanged. Okay, so 0 goes to 1, 1 goes to 0, or 0 goes to 0, and 1 goes to 1. So we're going to call the first 2 cases, we're going to call the function that generates the first 2 cases constant. So whatever input we insert, the function behaves the same way. And the last 2 cases are going to be called balanced. And what the question is when I have a function like this that maps 2 binary inputs to 2 binary outputs without knowing anything else about it, we need to determine whether the function is constant or balanced with the minimum number of evaluations of the function. This is a toy problem because if we think about the classical way to solve this problem, we only have to evaluate the function twice, so it's pretty trivial. So here's what a classical computer would do. It would say if f of 0 is 0, then if f of 1 is 0, then it's constant, and otherwise it's balanced. And if f of 0 is 1, then if f of 1 is 0, it's balanced, and otherwise it's constant. So we need 2 function evaluations to figure out the answer, and the question that Deutsch asked is, can we solve this problem more efficiently than that? So with 1 query to the function. Okay, so here's sort of the setup for this problem. So we have constant and balanced functions on a single bit. And the input, we're going to call it x, is a single bit. The output is also a single bit. And we have our 4 possible functions. So we have the constant functions, and we have the balanced functions. And when we run these through our quantum circuit, we need to take 2 inputs and generate 2 outputs. The first output is going to be unchanged by our unitary gate. The second is going to be modulated by it. So the way we need to think about how we modulate that second input is using this mod 2 addition. So this kind of plus symbol with the circle, that's basically an exclusive OR operation. It's a lot like our C0 gate. So 0 mod 2, 0 is 0, 0 mod 2, 1 is 1, 1, 0 is 1, 1, 1 is 0. Okay. So that's what our gray box is going to be doing to this function. Okay, so we have our 4 scenarios. So here's what the Deutsch algorithm looks like. We have our 2-qubit inputs, 0 and 1. So we have our starting state for our 2 qubits being psi 0 is 0, 1. And the next thing we're going to do is we're going to apply the Hadamard gate. So that brings us into the superposition state, psi 1, which is just 1/2 0, 0 minus 0, 1 plus 1, 0 minus 1, 1. So that's all familiar, straightforward. So the next thing we're going to do is only to the second qubit that's in the 1 state, we're going to do this mod 2 addition. And so there's 4 possibilities for the output. So if our function is 0, then nothing changes. We stay the same. If our function is 1, we flip qubit 2. If our function is x, we have sort of flopping of the second 2 terms, and if our function is x mod 1, mod 2, 1, then we flip the first 2. Okay, so those are all the 4 possible scenarios that we get when we do this, when we apply this function to our second qubit. So we can kind of simplify those 4 scenarios and rewrite that our quantum state after we get to this part of the circuit is plus minus 0 plus 1 square root of 2 times 0 minus 1 square root of 2, and plus minus 0 minus 1 over square root of 2 times 0 minus 1 over square root of 2. And the top case is the constant case, and the bottom case is the balanced case. So that's saying that the 2 balanced cases that we saw on the last slide, they differ only by an unobservable global phase. So that's our plus minus 1 out front. And that's the same for the constant cases. They only differed by a plus minus 1 global phase. Okay, so the last thing we need to do, so now we can kind of forget our second qubit there. We're not going to do anything more with it. So what we're going to do next is to the first qubit, we're going to apply the Hadamard gate. Okay? So that takes our first qubit states and it brings them to plus minus 0 and plus minus 1. Nothing happens to our second qubit states. So again, top row is for their constant function. Bottom row is for the balanced function. And now we're going to measure, okay? So the final step is to measure. And we're only measuring the first qubit. And so we can see the outcome will always be 0 if the function is constant, and it will be 1 if the function is balanced. So what's fun about this toy problem is, well, we only had to make sort of one query of the function. And we see that this idea of superposition and interference, in some sense, play kind of complementary roles. We prepare a state in superposition, we perform some operations, and then we use interference to discern some global property of the state. So this is a really simple problem. It's not very useful, so we're not using a quantum computer to evaluate something that's classically difficult, but we're using a quantum phenomena to reduce the number of queries we need to make to an unknown function to ascertain some information. Okay, so how do we take this a step further? And that's where Deutsch teamed up with Jozsa, and they said, okay, we are interested in kind of using this idea of balanced and constant functions and showing that we could actually do something useful with a quantum computer in the same kind of way that we just did with our 2-qubit building blocks. All right, so what the problem that they want to evaluate is quite similar. So you're given some hidden Boolean function f, and it's going to take as its input a string of bits, zeros and ones. So here's our function. It's going to take input zeros and ones, and it's going to output 0 or 1. And the function is guaranteed to be balanced or constant. And in the case of a function with multiple inputs, a constant function is going to return all zeros or all ones for any input. And a balanced function is going to return zeros for exactly half of the inputs and ones for the other half. And now our job is to determine, with minimum number of queries to our function, with minimum number of evaluations of our function, if the function is balanced or constant. So we can use a really simple analogy to think this through. So I buy a standard deck of cards, and in a separate room where you can't see me, I buy 2 decks of cards. I go and create a single deck of cards where either all the cards are red or all the cards are black, or half the cards are red and half the cards are black. So normal deck versus a stacked deck. And so now I go to you and I say, I want you to tell me which of the 2 possibilities is the case for the deck I just created. And you're going to do that by looking at the top card and then discarding it. So the question is, how many cards do you need to look at to decide if the deck is balanced or constant? So in the best case, the first card is one color and the second is the other, and you're done. So the deck must be balanced. But in the worst case, you have to examine. So if I was really mean and I put all of the red cards first and then all of the black cards, you would have to look at 27 cards. The first 26 cards could be black, and if the next card is black, then it's constant. And if it's red, then it's balanced. Okay? So that's the classical solution. If I have some function that has n inputs, then I would need to examine n plus 1 divided by 2 of them in order to answer the question. Okay, so how can we do this more intelligently using a quantum computer? How can we do this more efficiently? So to solve this problem, we're going to call up an oracle. And our oracle is just our function that we talked about in the Deutsch problem. So the reason that these are called oracles is because of the oracle at Delphi. So in ancient Greece, there were these high priestesses that were oracles, and in the right conditions, if it was like, the right temperature and the right weather patterns and all this stuff, then they would issue a prophecy. And there were other kind of lesser priestesses who would sometimes say, or give you yes or no answers to any question you asked. And so it's in that kind of second sense, the yes or no answers, that the notion of the oracle for quantum computing kind of came about. So an oracle is a function that we supply with some data, and it responds with a 1 for yes and a 0 for no. And that's it. And so for the algorithms that use them, 2 things are really important. So the implementation of the oracle has to be as fast and efficient as possible, and we want to call the oracle the fewest number of times possible to minimize the complexity of the algorithm. Okay, so generally an oracle is a black box, and its function is just to answer 1, yes or true, or 0, no or false. And we can express the inputs to the oracle function as a string of zeros and ones. And if we call the function f, we can express it as f01 raised to the n, some n number of qubits, gives you back 0 or 1. So this is a kind of long-winded way of saying, suppose we have a string of n zeros and ones, like 1, 0, 1, 1, 0, 0, 1, 0 for n equals 8. When I apply f to this string, I'm going to get back 1 if the criteria of the oracle is met, and I'm going to get back 0 otherwise. So, for example, if I have some quantum state, and I apply I'm going to get 1 back if some certain criteria is met. Say that quantum state is equal to 1, 0, 0, 0, 0, 1, 0. And I'm going to get 0 otherwise. So we're primarily interested in the action of the oracle on our standard basis kets. And in practice for quantum computing, we need to encapsulate the function of the oracle within a unitary matrix or gate somehow. And one way that we can do that is just to adjust the sign of a ket that meets the oracle's criteria for success. So let's look at what that might be like. So I'm going to encode the data we're searching through as standard basis kets, X. So if we have 100 data items, then we could use 7 qubits to do this, because 2 to the 7 is 128. And we're going to assign each data element to one of our basis kets. All right, so our oracle, F, is going to produce F of Y equals 1 for one special encoded piece of data, and 0 otherwise. So we want to find a unitary matrix such that when we apply that unitary matrix to X, we get minus Y if X equals Y. So consistent with what we said above. So F of Y equals 1, and we're going to get X otherwise. All right, so this means that our unitary function inverts the sign of the ket that satisfies the condition of the oracle, and it leaves everything else alone. Okay, so this was, kind of, maybe it was straightforward. Maybe you guys are following all this. But let me just break it down a little bit more. So we have 2 qubits, and we want the oracle to return a 1. If we give it a 0, 1, and a 0 otherwise. So if our quantum state is one of the standard basis kets, 0, 0, 0, 1, 1, 0, or 1, 1, then F of our quantum state is going to be, we're going to get a 1 if our quantum state is 0, 1, and we're going to get a 0 if it's 0, 0, 1, 0, or 1, 1. So our unitary function, U of F, needs to generate minus 0, 1 if our input state is 0, 1, and do nothing otherwise. So we could ask ourselves, what does a unitary matrix look like that does this? And right off the top of your head, you could write it down, right? So it would look like this, because we want to flip the 0, 1 qubit and do nothing to all of the, we want to flip the sign of the 0, 1 qubit and do nothing to any of the other ones, right? Okay, so depending on the algorithm and how we use the oracle, we might create some different unitary function, but it still has to reflect what the function tells us. And while we just thought of our unitary function as a matrix, we implement it as part of a circuit. And the trick is to construct it to be really computationally efficient. Okay, so if we go back to our playing card problem, we're asking the oracle, is the card at the top of the deck black? And it returns a 1 if it is, and a 0 if it's red. And like we said earlier, I would need to consult the oracle 27 times in the worst case to get the correct answer if I was just thinking about it in this classical picture. So if we continue to see the same output for each input we try, then we have to check exactly half of all the possible inputs plus 1 to be certain that our function is constant. And since the total number of possible inputs is 2n, this implies we need 2 to the n minus 1 plus 1 trial inputs to be certain that our function is constant in the worst case. That's pretty bad. So how do we do this using a quantum computer? So what Deutsch-Jozsa showed us is that we can solve this problem with one call to the oracle. And so here's the setup on the left. It looks a lot like the setup we saw for the Deutsch problem. So we have sort of a circuit that has n plus 1 wires, and n of those represent a register shown in the one I just bracketed. And we're going to initialize all of those bits, qubits, to 0. And then we have this extra wire here at the bottom. And this is going to be our sort of work qubit. We call it an ancilla qubit. It's not part of the input data, but we need it to do our computation. We need it to make this problem efficient. And it's exactly like how we used the second qubit in the Deutsch problem. But now we're using it in sort of a more complex landscape. So aside from giving us an extra place to put information, we can also initialize these ancilla qubits to known states. So algorithmically, we know the state of the ancilla, but we likely don't precisely know the states of the other qubits. And so in our circuit, we have our ancilla qubit Qn starting out in the 0 state, but then we use an X gate to flip it to the 1 state. All right, so how do we march ourselves through this circuit? We first prepare our 2 quantum registers, like I said, and the first one is this n qubit register initialized to 0, and the second is our 1 qubit register initialized to 1. So in our circuit, our starting quantum state, psi 0, is just the tensor product of 0 times 0 times 0 times 0 times 0, however many times, times n times 1. So that's our starting state. And then what we're going to do is we're going to apply Hadamard gate to each qubit. And so that brings us to some new quantum state, psi 1, which is just the sum over n of 1 divided by square root of 2 to the n plus 1 times x, I'll show you in a second, times 0 minus 1. All right, everybody's with me so far, right? Okay, so here's why I called it X. So we're going to call all of the quantum states after applying the Hadamard gate for our n qubit register X, and that means the output after we do the unitary is also X. And then for our ancilla qubit, we're going to call the quantum state at the end of that Hadamard gate Y, and so then the output after we do the unitary is just y mod 2 addition f of x. Okay, so the inputs, I just said this. Okay, so altogether, the input to our unitary is the tensor product of x and y. And the output is the tensor product of x with y mod 2 f of x. And f of x, we have to remember, always gives us 0 or 1. And so we can write down the state of our multi-qubit system after the unitary operation as follows. So we have the sum over n of 1 divided by square root of 2 to the n plus 1 times the same thing we had before, but now modified by this term, minus 1 to the f of x, okay, where f of x is 0 or 1. So put another way, we've encoded the effect of the oracle, that's our unitary, into the phase of each x state. And we've done this by multiplying x by a value of absolute value 1. So that's this thing. So a -1 global phase. And this trick, or this result, is something called a phase kickback, which comes up a lot in these quantum algorithms. And then remember, square root of 2 over 2 times 0 minus 1, that's just the state of our ancilla qubit in our second register. Okay? So that's just where we're at with that ancilla qubit. All right, so I'll just make a note. We've encoded the effect of the oracle into the phase of each x. Using this phase kickback trick. All right, so at this point, the second single qubit register can be totally ignored because we're done with it. We're not going to do anything more to it. Our string just ends and it's done. So the next step that we need to do is apply a Hadamard gate to all of our n qubits in the first register. And so when we do that, so we apply the tensor n Hadamard gate to our x states, we get 1 over square root of 2 the n times the sum over n of -1 times x times z. And we're summing over z here, not just to keep x's and y's and z's separate. After we, I guess maybe I should make the note. So this dot product here, x times z, that's the x0, z0 plus x1, z1 plus, etc. The sum of the bitwise products. Okay. So now what we're going to do is measure the first register. And what we see is that the probability of measuring 0, 0, 0, 0, 0, 0, 0 is -1 to the f of x divided by 2n, which evaluates to 1 or plus minus 1 if f of x is constant, and we call this constructive interference. And it evaluates to 0 if it's balanced. We call this destructive. So to see why this works, I think it's helpful to kind of break it down a little bit more. So our constant oracle, when the oracle is constant, it has no effect up to a global phase on the input qubits. And the quantum states before and after calling the oracle are the same. And since the Hadamard gate is its own inverse, so we applied it in step 2, and then we reverse it in step 4, we just obtain the initial quantum state in the first register. So that's easy to see. What about the balanced oracle? So after step 2 in our quantum circuit, our input register is an equal superposition of all the states in the computational phases. And when the oracle is balanced, our phase kickback trick adds a negative phase to half of the states. The quantum states after we query the oracle is orthogonal to the quantum state before we queried the oracle. So when we apply the Hadamard gates in step 4, we have to end up with a quantum state that's orthogonal to 0, 0, 0, 0, 0. And that means that we should never measure the all zero state. How is it faster? Well, this is all happening in parallel, right? You're only, you're taking one register and you're doing, so all your qubits are at 0, you're bringing them all to the equator, and then you're doing this unitary thing on a different qubit that you don't care about, and doing that operation down here, depending on what is going on up top, either keeps them all the same or adds a negative phase to half of them, depending on if the function is balanced or constant. And then all you do is bring them back, and you measure. That's it. I'm sure it's very fast in practice. And yeah, you only have to do sort of one step, well, 4 steps. But, yeah. So you do have to think very carefully about how you use that oracle. It has to be programmed very efficiently and effectively for it to be any faster, right? Like, you can do it really, like, there's always bad programming, right? That and you know, things can take, but there's also efficient programming, and one requirement to make this useful is that you program that part efficiently. Okay, so what Deutsch and Jozsa kind of laid out in their 1992 paper is that this gives us a way to potentially exponentially speed up this problem in a quantum computer. So I have Alice and Bob again, my buddies. And imagine that the oracle is held by Bob, who's spatially separated from Alice, who's trying to determine whether a function is constant or balanced. And to resolve an instance of Deutsch's problem, classically, Alice has to transmit 2 to the n divided by 2 plus 1 messages, each of a size of n bits, and each of which Bob replies to with 1 bit. But what the Deutsch-Jozsa algorithm shows us is that you only need to transmit a single n plus 1 qubit message to Alice, and then Bob can reply with an n qubit message. So there's an exponential reduction in the amount of information transfer required to solve an instance of Deutsch's algorithm using this protocol. So if we summarize briefly, what we've learned so far is that we can encode any mathematical function as a unitary matrix. That's cool. Deutsch's algorithm, the 1985 one, was the first algorithm that demonstrated a quantum advantage, even though it was a goofy toy problem. And specifically what he showed is that there's a reduction in the query complexity compared to a classical case, so from 2 to 1. And then Jozsa came along and challenged Deutsch and said, okay, we can generalize your algorithm to n qubits, or n states, and that revealed this possibility for exponential speed up using a quantum computer. And you can ask, is it useful? It's probably still not that useful, like this particular problem, but it's one of the foundational algorithms in the field that demonstrated this quantum advantage. So it's a really good one to learn the concept of the oracle on, because basically all the rest of them use it too. Yeah. So problems that require these kind of quantum solutions often involve components that can be tackled using classical algorithms, and in some cases those classical parts can be done on classical hardware. But of course, like this problem, for example, but in many cases the classical algorithms have to be run on inputs that exist in a superposition state, and that requires that the classical algorithm be run on quantum hardware. So that's kind of the unique thing. That's when that's where quantum computing becomes more interesting. So what we'll do I think we'll stop here today, and we'll kind of recap oracles in a little bit of a different lens next time, and then we're going to talk about Grover's search algorithm and then the Shor algorithm, but through the lens of the NMR quantum computer.